would like to have our chapter 5 lecture. So here's what I've decided to do. I am obviously not going to sit here and read to you like a bajillion PowerPoint slides. That's not happening from me. I've done the PowerPoint route for another class, but it was a much harder class and one that I felt they probably needed that really step-by-step situation. When I was in person and I did a stats class, one of the things I did for them, and they seem to really, really feel like it helped them, not just in math, but in college period, is I went through their textbook with them. Now, I am not going to go through your textbook in the sense of like, we're going to read every single line. Also not happening. But what I am going to do is I'm going to pull out what I think is super important. I have not looked at your test yet. In fact, I haven't made your test yet. So maybe I'll watch these myself and see what I think is really important. And then that will be part of what your test is, with the exception of the final. I don't make that. So let's dive into chapter 5. Let me tell you that first off, each one of these, almost each one of these, so groups, fields, and real numbers, groups and fields, and rings we aren't talking about either at the moment or not yet. Those are courses all in themselves. You can literally have a course in grad school literally called groups. You have one literally called fields, and you have one literally called rings. Discrete mathematics, you guys can actually take at LTRI-C. I forget what all the prereqs are, but you can actually take that with us. And it's, again, probably more of like an intro course, but totally worth taking. And then cryptography is also, can also be a course all completely on its own. In fact, somewhere, I don't know where it's at, but somewhere I have a book completely dedicated just to cryptography. So this chapter, really, really exciting, a lot of stuff. So let's dive in. Here's something I just wanted to show you guys because I thought it was really fun. So did anyone try to do this chapter challenge? I mean, it's okay because number one, oh, I probably should have showed you guys how to get into the textbook, but it's in the top of all your module, like at the very top of your modules. So highly recommend that if you're not understanding the PowerPoints by themselves, dive into the e-textbook, but I'm going to be going over that with you, so you guys don't really have to do that. So this is really, really cool. Do you guys want me to do the challenge at the beginning or at the end? It's up to you.
At the end.
At the end? Okay. So someone just remind me that you guys want to end with the challenge, because I just think it's really cool. I wrote myself a little note so that I hopefully won't forget. So what we're going to do first is we're going to talk about 5.1, which is natural numbers. Natural numbers are going to be the numbers that you guys think of like normal. So normal counting numbers, starting with 1, ending at as high as you can get. Those are your natural numbers. We can do, obviously, all of our operations with them, adding, subtracting, multiplying, dividing, all that fun stuff. Here's something where, remember I told you guys your class is going to be really, really fun because your course is going to take things that you're used to playing around with and used to working with on maybe a day-to-day basis, and it's going to make you look at it and go, why are we thinking about it like this? But that's part of the fun. So I want to make sure that you guys understand this closure property. Closure is when we have a set, and if I really actually like this analogy here between a closed box versus a box that has the top open. Okay, so with the closure property, it's saying that anything that could possibly be inside that set is in fact in that set, and there's nothing missing. When you have an issue with closure, it's saying that there's an element or possibly multiple elements that should be in that set and they're not. So if you look at this example, it says, is the set A, and then it tells you what's in the set, closed for addition. So if you guys look at that, and you can see the solution they tell you is that set A is not closed for addition because 5 plus 7 is 12, and 12 is not an element in A. That's what this E symbol with a slash means. It means it's not an element in A. How do you think you would make that set closed?
I presume you'd add more numbers to it.
Yeah, so you'd have to include the missing elements. So right now we know that 5 plus 7 is 12, and that's missing. We know that 1 plus 10 would be 11, so that's missing. You'd literally have to find all of your additions given that 1 through 10 set and make sure that all those elements are also included. Once you make those changes, then you would say that set A is closed for addition because all of them are represented. Does that make sense? You can give me head nods, you can give me
Yes.
physical thumbs up, you can give me reaction thumbs up. If it's a thumbs down,
Yes.
don't be afraid to tell me no, okay? So definitely, it's okay if you don't understand it. You just got to let me know. Okay, so the next thing that we're kind of going to look at is checking for understanding of commutative and associative properties. I assume at this point you guys are all kind of good with this. Basically, it's a nice way to make things a little bit easier for you. So, if
Recording
you
in
come,
progress.
that was weird. That's never happened to me. Oh well, YouTube can hear recordings in progress, as if they didn't know. So what we notice here is if we have a vertical line that we want to add, obviously if we took it as 9 plus 8, and clearly, these are a little bit simpler numbers that we're working with, but the practice makes sense nonetheless. 9 plus 1 is a lot easier than 9 plus 8, right? Like your brain's going to see 10 a lot easier than it's going to see 17. So if you did it like this and found these nice groupings of 10, then it's going to take you a lot less time to add all of that than it would if you would do each set as you see them. Okay, that's all that's basically telling you. Multiplication. I mean, we all understand multiplication. We know that if one of the numbers is 0, then the result would be 0. So closure for n, when we're dealing with multiplication, it's going to be the same thing. They're going to give you, I'm going to have to figure out that setting because I don't like it. So they're going to give you another set. And in this case, it's just 0 and 1. We know that if we multiply 0 times 0, we have 0. 0 times 1, we have 0. And 1 times 0, we have 0. And 1 times 1, we have 1. There is nothing else that we could have in that set of B that is not represented. So everything's in there. All right? Okay. And what's great about your class is your class will be different every week. So we're definitely going to be going through some of the stuff. Let me pull this over to here. Oh, okay. Can everyone else hear me? Yeah.
Yes.
Okay.
Yep.
Cool.
Yep.
Yeah.
All right, cool. Just wanted to make sure. So, because I would hate to put up a video that was me just talking and looking mute. So distributive property. This is the one that your textbook considers the most important. Possibly because it's just maybe the hardest to wrap your head around, but I feel like if you understand multiplication in general, then you should understand distributed property in general. But if we look at it in terms of, nope, they did not give us a decent example. So this is interesting, right? So if we don't follow our rules here, we can end up with two very different numbers. Okay. So just kind of pay attention, but I feel like you all are good with distributed property. All right. Subtraction. Again, this is like the most I could understand them giving you would be another set. Yeah, and you would just have to do the same thing you did for addition, but with subtraction. Okay. Now, one thing I will caution you is right now you're dealing with natural numbers, so you're counting numbers. In what section? In section 3, we're going to get to it. You're going to talk about integers. So you have to be careful with subtraction because right now, if you're looking in if your universe is just section 5.1, there should not really be any negative numbers involved. It should just be positive outcomes, even though you're doing subtraction. Okay. And then the only thing I want to really note about your sets, your problem sets in your ebook is one, a lot of the problems might look familiar to what's on your homework. So if you're having a hard time figuring out your homework, you can always come into your ebook and they have all of the answers available to you. They also might be able to kind of link you to where those questions are coming from the ebook, so you can like read that a little bit. I think it's also in your homework set up that way as well. So your ebook can be a definitely good resource for you. The other thing I want to show you is at the very end of the chapter. So I want to give you guys a bonus opportunity. Okay. All right. So prime numbers. Okay. Divisibility. What do you think the big confusion could be with divisibility? What do you guys think it could be?
Dividing into decimals.
Yeah, so if you take a look here, divisibility is actually a little bit different of a symbol than division. So when we use division, we use a slanted kind of like slash. When we're talking about divisibility, we're stating that we know that 5 divides into 30. So we actually use an up and down straight symbol. And that's kind of where that difference falls into. You should never really have a decimal come out of a divisibility. It's either gonna be a yes, this is divisible, or it's gonna be a no, this is not divisible. So none of those, so if you're getting a decimal, then your answer really is false. Like that's not a true divisibility statement. So that was good. Good job. Okay. I want to show you guys this table. So it might be kind of hard to see. I don't know if I'll be able to move this. Nope, that just changes the page. Give me a second. If I move that over. Can I move this a little bit more? No, I guess not. Okay, so I can put this, I think, bigger on canvas. I'm going to snip it. Okay. So can you guys see that for the most part? All right. So what this does is it gives you some rules for divisibility with natural numbers. Obviously, one is able to be divided into all numbers. And then it just gives you little test tricks. I thought it was really nice. So I'm not sure if you'll have homework problems with it. I'm sure you will. But this little table, you can definitely, like, if you wanted to, you could make little flashcards. I mean, some of it you might already have memorized. So obviously we know that any even number, anything that ends in an even number is going to be divisible by 2. The trick for 3s is if you add the numbers up in the digit and that number is divisible by 3, then the large number will be divisible by 3. So it's just those kind of things I think they're kind of neat. So I wanted to pull your attention to that. Okay. So that is not the end. I thought it was. Yeah, it definitely is. That was no. All right, whatever. Maybe I just wrote my stuff down wrong. So finding primes. Who can tell me what a prime is?
Man, I used to know it too. It's like numbers that don't get divided into, but divide into other numbers.
Close. Anyone have a little bit different of a way of saying that?
I might be wrong, but is it a number that's only divisible by itself?
Very close. Ember, what was your, how are you gonna say?
One and itself.
There it is. So numbers that are divisible only by 1 and itself. And yes, Zach, your idea of they can be divided into other numbers is kind of true, because we know that, like, for instance, 3 is prime because only 1 and 3 go into it, but 3 can divide into other numbers. It's just not really used for the definition. Okay. So we can also use this super cool thing called a sieve. And if you follow the steps of the sieve, which they're right here on, I don't know what page this is, but this is the steps for the sieve. Basically you write down a list of numbers from 1 to 100, and then you follow this process. And then what you have left will be the prime numbers from 1 to 100. And you don't even have to, like, think about them. Like, you don't have to do the test. You don't have to do any test for divisibility. You just literally follow the sieve and it gets you all of them. So that could be kind of like a cool trick you could play, like at a game night or something. You could literally be like, hey, I bet you I can list all the prime numbers between 1 and 100. And your friends would be like, no, you can't. And you would just spout them off if you memorize this list. So I don't know. I thought that was kind of cool, and I wanted to show you guys that. Prime factoring. Okay, this could be something that you should hopefully have done in the past at some point. And basically, if you don't remember how to do it, that's okay, but this will hopefully bring it back to your memory. You want to get the number down into its prime components. Okay, makes sense? So if we take 5 times 7 times 11, we will get back to 385. But 5, 7, and 11 are all prime numbers. Okay, so we have factored it down to its purest prime forms. Okay. Right, and then I really like how your ebook has these little videos in it too. So it might definitely be worth it for some of you to dive into the ebook. So again, let's take a look at this. This conical representation is literally just another term for prime factoring. Here's the difference. Do you see how they have the little exponents here? Okay. So, not really sure the point of the 2 being there. I guess it's because, so 2 is your first prime number, right? 2 is your smallest prime number. If it's not there, 2 raised to the 0 power is 1. So it doesn't change that prime factoring. Okay. And then you want to state how many 3s there are. So that would be 3 squared, 5 to the first, 7 to the first, 11 to the first. That's where you're getting this conical representation. And that's the difference between it and prime factoring. Does that make sense? Okay. Prime factoring can help you find your greatest common factor. I'll be honest, unless something asks me for that, I kind of forget about greatest common factors. I just
Do
go with
you
Hmm?
do you have to add the exponent of 1 if you know every whole number do have the exponent of 1? Like, or is just something that kind of like demonstrate to make you understand that it just have the exponent of 1? Just
if you don't have to do it in this canonical form, then you can just write it down like normal without the exponent of 1. If it's asking specifically for this conical form, you have to have the exponents. So even if it's the understood 1, you need to have it.
okay.
I think that's where the difference comes in between that and prime factoring. Okay, so that is it for that part. This was kind of fun, and I think you guys, if you decide to do the bonus opportunity, will probably want to come back to this page. It's kind of more like how mathematicians in the past pursued prime numbers. For a very long time, prime
How do you
numbers,
pronounce his name?
this guy's name,
Yeah.
no idea. Old dead white guy. That's
Yeah,
what
I was kind of like,
that's how I pronounce most mathematicians' names. Yeah, if I tried it, I would probably just butcher it. So, yep, we'll go with
that's right.
yeah, we'll go with that. I will never, ever, ever ask you for a mathematician's name. I understand that, you know, the common way of teaching some things is like, oh, well, you should know Euclid and you should know Pythagorean and all this other stuff. I mean, I showed you the processes. That's what I care about. I'm no longer in the mindset that everything has to have someone's name attached to it. But I mean, obviously, if I were writing a paper, I would give it to them. And this is another one for Matt. He was a French mathematician, and I mean, he came up with Fermat's little theorem and like all this stuff. Like prime numbers for a very, very long time were the like epitome of what you did when you went into mathematics. If you want my honest opinion, it's because back in the day, like way back in the day, like we're talking when people sat around just literally eating grapes and philosophizing about things, they had nothing else to do. They either worked fields, they made some wine, they maybe tended some other fields for some other animals, and that's it. That's all they had to do. Like, so why not spend time talking about numbers? I mean, is it a great thing that they did for some of us who are now spending their lives doing numbers? Absolutely. Would we right now be able to just dedicate tons and tons of time to sitting around talking about prime numbers? No. We have to worry about how we're paying our bills. So, but that being said, prime numbers are still a hot topic because there's still so much we don't know about it. So right here's a prime example. No pun intended. Totally can't believe I just said that. We still don't know if there is a largest prime. or if there are infinitely many primes. We don't know that. So we have theories, like this mathematician came up with a theory that there are no largest prime. But I mean, did he really prove that, or is that just his like idea and this is what he came up with? So I mean, we just don't know that. All right. So we are done with 5.2 in terms of my discussing it. So integers. Again, we can do everything we normally can do, all of our operations, adding, subtracting, multiplying, dividing. We can now throw in absolute value because integers now include 0 and negative numbers. Okay, obviously we wouldn't have a need to do absolute value with our counting numbers because everything's positive. But now we can bring in this idea of absolute values. And you guys know that if it's no matter what it is, unless there's a negative outside the absolute value, you're going to get a positive out because it's the distance away from 0. Okay. And if I go too fast or if I'm not explaining something to the point where you guys are happy with it, just let me know. I can always come back at the end because I'm sure we'll do a Q&A at the end. Right. So addition of integers, the only thing I want to point out to you, like the caveat or the caution that I want to give you is remember when we're adding integers, you can have negative numbers and you can have positive numbers in a mix thereof. So what you want to remember is if they're both positive, that's like adding your regular counting numbers, you'll get a positive out. If they're both negative, you'll add them and keep the negative sign. If you have one that's negative and one that's positive, it depends on which one is higher. So in C and D here, we have a positive 41, but a negative 13. Negative 13 in itself is lower than 41, so you'll just subtract. 41, on the other hand, when it's negative, again, 41 is greater than 13, so you'll have a negative outcome. All right, so just wanted to re-solidify that in your brains in case anyone has forgotten. Multiplying integers, same basic thing that I want to go over is the signs. If you have a positive times a positive, you'll have a positive. Negative times a negative, you also have a positive. And then negative or negative positive, you're going to have a negative no matter what. All right. Subtraction of integers. Again, what you have to realize here is that sometimes you can have a negative negative. That's going to change it to a positive. All right. All right. Division of integers, pretty much the same, exactly the same with the multiplication in terms of your signs. So honestly, guys, if you can remember your signs, then you'll be good for that whole section. The only other thing I want to bring to your attention is that you cannot have 0 as your division. So you can divide any number by 0 and you'll get 0, but you can never divide anything else by 0. It would be undefined. Or I guess for your book, it's saying it's not permitted. Okay. All right. All right, that is the end of what I think is important in 5.3. So that brings us to rational numbers. Rational numbers are what? Does anyone remember? Okay. Rational numbers are fractions. Okay. They are basically going to fill in where everything else we've left out of what we've been talking about so far. So what I want to go over here is the fundamental property. Basically, it's telling you that if you have A over B and you multiply top and bottom by the same thing, Doesn't matter what it is, as long as it's the same. And it also doesn't matter the order. You're still going to have A over B in the end. Like, so I use this a lot in intermediate algebra. When I need my students to see, like, if I have a fraction and then I'm subtracting it or adding it to a whole number, that whole number can be represented with the same denominator as long as we multiply top and bottom. So that I use this all the time. My students just don't know the name of it. Okay. We can also have operations with rationals. If you guys need help with this, just shoot me an email. I probably have a video already made, but I can make another video of your operations with fractions. That should definitely be something that you guys are coming in with the knowledge base of. But again, if you need like a refresher on how to do some of this stuff, I will obviously not include an example that's this huge. Not going to do that. Just going to do your basic understanding of the operations of fractions. Okay. All right. Irrational numbers. Now we have pretty much have covered all of your like the whole gambit. Anything you can now think of has been represented between those 5 sections. All right, your counting numbers, your rational numbers, your irrational numbers, your integers, everything is now covered. Any number you can think of, you have now covered it. Speaking of mathematicians that I will say their name every once in a while, Pythagoras came up with Pythagorean theorem. And to bring our minds recalling what that is how we find the sides of a right triangle. So a squared plus b squared equals c squared. There are other, I guess basically you would say, applications of Pythagorean theorem. People just don't normally typically see them every day. Here you can see they kind of use a different representation to prove to you that Pythagorean theorem does work. But yeah, I mean, if you've used it before, cool. If you haven't, again, we can go over it in a video if you need me to go over that. Square roots, you guys should be okay with those as well. When I teach square roots in other math classes, I basically teach it as you have to pay the ferryman. So if you are doing square roots, then you have to have 2 of that item to get out, but only 1 person gets out. So that's why I picked the ferryman, because you really can't be escaping the underworld, right? So he's only going to let 1 of you out. Probably a little bit morbid, but they remember it. So, okay. Operations with square roots, again, I can do that in a separate video, because some of this stuff I think is just stuff that most of you should recall. All right. So 5.6, 5.7, and 5.8. This is the super fun stuff that you now are going to be having to use those ideas of rational numbers, irrational numbers, everything we just talked about in the first section of chapter 5. Now we're going to be doing different things with them. And now your brains will probably go, why are we doing it? Super fun stuff. So, definition of real numbers. The set of real numbers denoted by, so when you guys have taken algebra in the past, if you had an all real situation, you wrote like that fancy R. That is what real numbers are. It's literally everything. The union between rationals and irrationals, everything you can think of creates the real number set. Okay. You want to review how to convert from fractional form to decimal form and vice versa. They have nice little videos, like I said. Okay. Yep. Identity and inverse properties. So, the identity for addition, 0 plus a equals a plus 0, which is just a. That's literally it. That's your identity for addition, or your additive identity. Knowing that, what do you think your identity for multiplication would be? Anybody?
What does identity mean for addition?
So identity means like in its purest, truest sense, how would you describe adding to someone? So in this case, an identity is always going to have something where you have, for instance, a equals a. So for addition, that one thing you can add to all things that doesn't change its value is 0. So for are you giving me the answer for multiplication?
Yeah, would it be 1?
Yes. Okay. So for multiplication, you're going to have 1 times a equals a times 1. And then for subtraction, of course, I'm pretty sure it would also be 0. Yep. Oh, they skipped it around on me. That's why. So what they care about next is your inverse property for addition. So when you're looking at that, you want to ask yourself, what do I do to get back to nothing? Well, you have to subtract the same thing. So a plus negative a or negative a plus a will give you 0. Right? The inverse for multiplication then, so you can look at this 2 different ways. You can either use the exponents, which they're using there, but here's the other thing you can do, the other format. You could do a times 1 over a, right? Because the a's will cancel. So that's basically what they're showing you there, but they're choosing to be more mathy by using the negative exponent. Okay. All right. You guys have any questions on the identity stuff? You basically just need to figure out what same number can you use to get you to the goal. Great. Groups and fields. If you're going to get confused on anything in this chapter, it's probably going to be the groups and fields stuff. It's just like I said, a different way of reading stuff. So for instance, here for this group, it's saying closure. And then we have A, and the operation of B is an element in S. Okay. And then we can also do the same for associative. We can do one for identity, inverse, like whatever you can think of, you can make a group out of it. You just have to then say that they're an element of how you basically can make the rule. And as long as you make the rule, and then everything that you have to worry about is everything in the group that should be in the group. Natural numbers do not form a group. So is the set n of natural numbers a group for multiplication? So let's look at this example. We have already studied the properties of n, so we can form hasty conclusions. Okay, so just kind of, I would just play around with some of these examples. They're definitely going to help you with your homework, because I can already, like, just from looking at your homework briefly, they're definitely on there. And then if this is too small for you guys to read, I can also try and make it bigger for you. This is talking about fields. And if you look at the definition here, a field is a set within the all reals with two operations, plus and multiplication, satisfying the following properties for any elements A, B, and C that are an element within the all reals. So honestly, it's just playing around with numbers. That's all it is. People literally spend entire semesters diving into this stuff. Two different classes, and then rings is a third one, which we're not even touching on right now. So this stuff can get very, very heavy. So don't let yourselves get wrapped up in that stuff. Just kind of understand the basic definitions, and you should be good to go for your homework and your quizzes. Right. Again, you guys can always look at your problem sets in the textbook, in the ebook, to help you with the problem sets that you have on Canvas. Nope. Well, Canvas into WebAssign. So the discrete math, did anybody have some issues maybe with this section when you were looking at your PowerPoint notes? Okay. Right. I can definitely still field questions after we've wrap up these last two sections. So clock arithmetic. I can tell you guys that I do the vast majority of all of the clocks in my house. Clocks, watches, cell phone, anything that I have personal control over is on military time. The 12-hour clock system to me is just dumb. I don't think there are 2 hours repeated in a day. So why should it be on my clock like that? Because my brain's already set up for military time, I was able to understand these examples a lot quicker. So if you're someone who's used to military time, you probably caught on to how to do the arithmetic clock math a little bit quicker. And if that's something you understand and can help your peers do, then you should definitely help them out. The other thing in this section is this modulo math. Modulus math is literally another thing that you would find in, say, abstract algebra, and it's you can go for chapters with it. It is a lot of information. Basically, in its most simplest way to understand, a modulus is having you change how many numbers you have available. Does that make sense? So like right now, when you have a modulus of 1, literally, it's every single number you can possibly think of. Okay. When you do a modulo of 5, is it here? Yeah, it's here. So here's the addition and here's the multiplication. We're just going to focus on the addition for the moment. Do you see how it's 0, 1, 2, 3, 4? That's because how many actual numbers is that? 0, 1, 2, 3, 4. 5. Yep, 5. So when you're with a modulo of 5, when you get to the number 5, you start back at 0. Like so really when you do this, where's that example was on someone's homework. So let me write it off to the side. Okay. So if we have a modulus of 5, so 0, 1, 2, 3, 4, this is how you want to do your homework. If we are doing this 4 plus 9 thing, okay, 4 plus 9 would be 13. You would literally would go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Do you see how 9, what's it really land on? 3, right? Yeah, good. So when you will have a problem, I think it's on the PowerPoint, and the problem said something like 2 plus 1 equals 3 is not the same as 4 plus 9 equals 3 in mod 5. Okay. And I believe the point they're trying to show there is because even though the outcomes are both 3, the mods are different. Okay. So 2 plus 1, you can see that that's in this modulus, like this set right here. This set right here, you would find that if you just regularly started counting, right? 0, 1, 2, 3, 4. That's your normal way of counting. 2 plus 1 falls into your normal way of counting. If you were normally counting, would 4 plus 9 equal 3 to you?
No.
No, no. But if we're doing a mod 5, 9 doesn't exist and neither does 13, because you have to rewrite it in terms of this mod 5. So that's why this 3 is very different than this 3. Make sense?
Yep.
Cool. Good. All right. And if you guys do need that kind of gone over a little bit more at some point, feel free to bring it back up when we do our review for the first exam. Definitely, I can understand if some folks need that a little bit more. And just honestly, just have fun with it. Just play around with it. Like, so now you have that basis for mod 5. Maybe try doing some problems in mod 6. Like, you can do it with a whole bunch of like literally any number you can think of can have a modulus. It just would make it a little bit different. So here this is talking about test group properties for modulo 6. So you can look at that. Again, testing properties for mod 5. So the book really helps you break stuff down. I think it's a decent book. So cryptography, very fun things here. Any of you who are interested in like potentially going to like the NSA, some other government contracts, you will have to do cryptography all the time. And it's basically ciphers and codes. And what we are going to do is going to be vastly simplistic versus something you would do with more advanced computer coding and ciphers for that. And I believe on your homework, and I'm pretty sure on your quiz, I think I gave you at least one, if not 2 fun ciphers to do for your quiz. You literally figure out your what you call, so like they give you a hint. Then from that hint, you have to figure out your key. And then once you have your key, you can start figuring out the cipher. Okay. I'm going to let you guys actually have some fun with that. I thought they were some of the greatest things ever when I was first learning how to do stuff. And literally I went out and bought, like, I'm not telling you guys to buy anything, But I went out and I bought a book like at the bookstore that was literally 101 like cipher puzzles or something like that. I promise you it was literally a waste of money because I didn't end up doing anything with it. I just kind of carried it around in my backpack, so my professor thought I cared about it a little bit more. But I mean, it's fun stuff. I think it's really fun stuff. And then as if codes weren't like, so that this to me is the fun version. Okay. This is the kind that everyone should be able to wrap around as long as you have the key. This is the kind of stuff that like they have you do maybe as time fillers whenever you're like right at Thanksgiving or Christmas vacation in you know, primary school or whatever. They're like, here, try to figure this out, and you spend like, you know, 6 hours on it, and you finally get happy because you get one word. Now we take what we just did with modular math, and we can actually apply it to a code. Okay. So if they want you to encode, in other words, make it so that you are given now the phrase, the FBI has bed bugs, and now they want you to put that into a cipher, and now they want you to make the coded part. And they tell you how. They say use modular 29 code. So that's literally what this little representation is. And I would definitely go through and try and figure out this for yourselves. So T, literally, if you follow around, the T is the 20. Okay, but T could also be 49, and I guess T could also be 78. So it's a pretty interesting, fun little example there. And then here they give you one to work on as a decoding. Okay. So again, if you're encoding, you're given the message and you need to give them something that if you, let's say you and your best friend want to have a secret communication and you don't want your sister to find out, then you send your best friend the encoded part, and then they would have to decode it to see what you were saying. Okay. I know that's kind of like a juvenile example, but I don't know, change it to best friend and partner or whatever. Like maybe you have a partner who's like, oh, you can't ever surprise me with what you want to get me for Christmas. I know all of it. I know all of it. Okay. Then maybe you could do something like that. It would actually be kind of funny. All right. Unbreakable codes. I do want to point this out to you guys. Why do you think it would be a good thing? And why do you think this anagram, which some of you in computer science stuff probably have heard of as an RSA, why do you think it's important to have an unbreakable code? What do you guys think?
To protect data?
Yeah, exactly. Yep. I'm trying to think. I wish I had something up right now that had it, but like you guys know, on websites where, let's say you were looking to see if something was like okay to put in your information, you know, sometimes like an application will be like, please insert your social security number, and everybody with their social security number is like, maybe I should not do that, right? Especially with your especially with your social security number, right? So, but if you look on the website, at the very beginning of the URL will be this little lock. It'll literally look like a lock. So that's supposed to let us know that we can breathe a sigh of relief, because that little lock is telling us that we are okay. This is a secure site. Although I'll tell you a little secret about that little lock. As much as it's a secure site, it will still breed spam emails and phone calls. So just be careful. by the way, this is the cryptography book that I have. I found it. I put it next to your book in case I want to pull any examples from it. Again, not that you guys would have to ever buy that. I might even be able to find it as a PDF, honestly, if you guys were interested. But so I'm going to